talk about the problem set. Let's go into it. So we want to first explain what is the difference between a decidable and recognizable language. Decidable language is a language that we can create a Turing machine for, that can recognize if a word is in the language. So a decidable language is a recognizable language that we can reject if it's not in the language. This has some important implication that if a language is recognizable and co-recognizable means that the opposite of the language is also recognizable. If we have these two, it means we have a decidable language. So every decidable language is also recognizable. So the problem for now is, if we have a variable in the CFG, in the context-free grammar G, we want to know if there is some word that we cannot create without V. This is called the variable necessity problem, and this problem is undecidable, but it's also recognizable. But CFG is first. So unless there is some loop that, let's say we start a variable x, and then we go back to x without making any effect in the string, we would have an infinite number of ways to derive a specific word, because we can loop however many times we want and there's no effect. But let's also notice that a loop is not itself necessary. This kind of loop is not necessary, because we can just not take it, which means if V only exists inside the loop, it's not necessary. But if we remove the loops, it means we can derive a word in finite number of ways, because each rule will make a change in the string, and if we are making changes, it means we are changing the length, we're changing variables. So at the end we will have to either reach the word or not reach the word. So if we are going to skip checking derivations that use the loop, which means that if there is a derivation we can do, but there is another one with the loop, another one with two loops, and the other one doing the loop 100 times, we skip the other ones with the loop and only do one of them. So how are we going to do it? So if we go for every word in the language of G, then do all the derivations of V, we can see if all derivations have V. So if there is a word, if there is such word, after a finite number of time, after we keep checking one by one, we will eventually reach it. If there is no such variable, if there is no such word, we will never reach it. So why can't we decide it? So let's talk about another CFG which is important for this discussion, which is called the universal CFG, which is a CFG that can, by the way, CFG stands for context-free grammar. I just say it because it's shorter. So a universal CFG is a CFG whose language is all words that's possible. Our notation is called sigma star. So a universal CFG, the language of universal CFG is known to be undecidable. We cannot decide it. However, we can show that this necessity problem, if we can solve it, we can solve the universal CFG problem. So how can we do it? So let's say we make a new CFG that can generate all the words. We can do that. So we can generate all the words with a variable called V. And then let's connect the CFG we want to detect. Let's say it's called G with this CFG. So we can see two parts. So the start variable of the all CFG, and the start variable or the G we want to check. So here it uses V to generate all the words in the alphabet, and we can also have an option to do the other CFG. So this means we can either generate any word from this way, or generate all words in the CFG. So what does this mean? So this means that if the variable V is necessary for some word, it means we cannot generate it with the CFG G, or we cannot generate it with G, because V would be the only way. We generate every word in with V and generate all S without V. It would be also nice if we change the variable names in S of G to make sure there is no V variable inside, just to not disturb this logic, because we are assuming there is no V inside S of G. So yes, this is what we are talking about. So we showed that we can use this Turing machine to check if is necessary. It means G couldn't create it, but if V is not necessary, this means that V wasn't necessary to do any word in the language, which means that the CFG G was able to create all of them, which means its language is all the possible sigma stars. So this obviously contradicts what our original what we know, that universal is undecidable. So the assumption is wrong. So how does this affect our everyday life? So we know we have compilers that recognize languages and give us sometimes errors and find maybe even knows even how to fix the code. So this requires the language not only be recognizable by the compiler, but also to determine if it's incorrect. Because if it's able to recognize correctness and able to recognize incorrectness, it means it can decide the language. So every coding language must be designed with this in mind. The language must be decidable. So also about automated reasoning, computers are the practical version of Turing machine. So if a Turing machine cannot decide a problem, a computer will not be able to. So let's say we have a problem that we need to do, but the problem itself is not decidable. So we know we cannot do it. So there is another way to a workaround this is to have a time limit to prevent it from running for a long time. Because let's say even if it's decidable but it takes 100 years to do so, it's not really practical. So let's say we have a time limit 1 minute to solve the problem. If it doesn't, then we reject it. It's kind of a way to solve undecidable problems. Yeah, that's all. Thank you.